In this video, we will talk about digital and analog systems. Alright, but first we will talk about three things. Alright, in this video, we'll talk about three things. The first one is the concept of continuous, discretize, and quantize. The second one is the analog and digital benefits. Why do I change to digital? Alright, the last one is that digital itself has a limitation of resolution. And therefore, what does all this mean shall be explained in this video. And to start off, we will start off with the definitions of continuous, discretize, and quantize. And this is why the reason behind why I posted this video first at this playlist is to introduce you with all the stuff. I will still explain it over here, and you can just watch all this playlist from this guy. So, and therefore, if you know what is continuous, discrete, and quantized, you can just skip. Otherwise, you can just take a look. Alright, imagine I have a signal. Alright, with certain 1, 2. Definition of continuous time signal is that if you were to take a look in this zoom in version, if I were to zoom in into this portion over here, so if I were to draw it in a more zoom in way, I'll have a representation of this piece, of this piece of a signal, and this piece of a signal is over here right now, and then it can be represented by all this, minus 2.4, this is minus 2.6, etc. Now I'm looking into, I zoom in again, I look into this portion over here, this portion of the signal, I go over here. Now I'm talking about minus 2.5 and minus 2.4 of the signal, which is somewhat like that. Alright, and then I can also go in again. This is minus 2.45, and then this is minus 2.44, and then I can zoom in again. Alright, so we can keep zooming in, and this signal is always continued. Alright, there is no breakage. For example, it stops, it comes here, and then it connects back to the other one. It's not a, so therefore there is no breakage over here. Alright, so continuous is a signal that continuously moving. Alright, it's called continuously captured, or in this sense. Alright, and therefore what is actually digital? Alright, or in other words, discrete. I shouldn't call it digital, I should call it discrete. Sorry, discrete, and that it is also called sampling. Alright, sampling states, or discrete states that, alright, at this point, I take this signal, and then at this point I take this signal, at this point I take this signal, as you can see. So how many points I can take? Alright, in this case I take in terms of unit of 1, because minus 2 to minus 1 is just unit of 1. Alright, so I'm taking in terms of unit of 1, and I can re-represent this graph itself, alright, as a series of algaes of don't know what, but yeah. So you can represent this thing, this signal over here, this black color signal, as simply this one. So I can just draw it out again, somewhat. Alright, so it's somewhat nearest to the actual signal itself. Alright, and if I were to take more samples, instead of just minus 2, minus 1, I'll take more samples. Alright, I'll take more discrete samples. If I can in so-called increase the number of sampling data, then I can better represent my actual signal, right? Yeah, so this signal over here will be more so-called better represented in some sense. So more points will better represent the actual signal. That's what I'm trying to say lah. Alright, although I didn't draw properly in this sector. So I will better represent this signal. If you were to compare this one and to this one, alright, this signal is simply just like that. If I were to draw just now as I drawn, if I take more samples, I can better represent the data like that, the signal, which is more nearer to the actual signal. Hope this is pretty straightforward. Then we'll come back to here. Now we go to quantize. And therefore, what is quantize? Okay, what do you mean by quantizing a signal? Quantizing a signal is similar to discrete. We're taking each of this point right now. Once you take each of this point, this is what I'm talking about as discrete, which is what previously we were talking about. Quantize, if I were to say it, alright, is in fact somewhat like a round off. Round off means that, alright, if you were to take a look, this signal is somewhat 1. Okay, this signal is perhaps 1.7. Alright, or maybe I will say that this is round down. Alright, if it's 1.7 over here, if I were to zoom in, okay, if I zoom in over here, at this point is about 1.5. Okay, so I would round down as 1. Okay, I will still say that this is actually at this point. So quantize itself is somewhat rounding down. Alright, likewise this is at 1, so it's okay, so I'll just say this 1. And then at this point, alright, at this point, this is 2.5. I say it's at 2. Alright, I quantize at 2. So if I were to quantize it individually, maybe I should write the quantize at this point. The red color are the quantized one. Maybe this is 3, and then this is also 3. So a quantized signal will be somewhat like that. Alright, somewhat nearer to the original signal in the black color, right? However, quantize itself re-represented the signal in a different way. Alright, if you were to take a look in terms of the orange color signal, then the orange color signal is the digital one. The digital one is something like that. Alright. So if you were to compare, then digital one is just simply sampling. Alright, quantize is simply rounding off. If you were to compare accuracy, quantize is lousier than the discrete signal. Alright, so I repeat again, the continuous one is simply a continuous signal. Alright, and then next we talk about sampling, which is also calling the discrete system, where we only sample each of a certain point of the signal itself. And then going more further, we can round off each of this point and to a certain beta sig and we call this a quantize. Why do we round off? Okay, when we take a certain sample, for example at this point, alright, at this particular point, we say that it's 1.5. Right, it may be 1.532 8, 9, 7, 3, 4. Alright, it may be all these numbers, and the computer may not store all these numbers. So what they can actually do is to round off, or round down to the more better representation. So therefore it's 1.5. Alright. And then in terms of the rounding, it can be round up or round down. Alright, I don't know whether am I saying the correct stuff, but it's still going to round up to the or round down to the certain values. So in other words, they will just round to a certain value, up or down. It all depends on how it's being designed, I would say. And therefore, how do we link to analog to digital benefits? Alright, how do we know that which is analog, which is digital? Okay, analog itself is, if you remember, analog itself is just some temperature. It can be a certain velocity or whatever, or it's in something in the real world. Alright, so we're gonna change something in the real world to a digital world, and the real world itself is always continuous. Alright, the temperature is flowing. Alright, it's always flowing continuously. You don't have any stop points and things like that. And therefore, analog is simply continuous signal, which is always there. Alright, So if you want to change the analog system into a digital one, alright, we can process them in terms of the sampling and the quantized method that we have said earlier. Alright, so the discrete and the quantized are all inside this digital manner, and analog is simply the continuous. And to digitize this analog system or the continuous system, alright, we can actually correlate noise, alright, or have a more stable signal. Okay, so somewhat you can filter out all the noises. So I'll not go into details, but this is just the brief benefits of analog to digital benefits. But however, one key thing is that the digital itself has limited resolution. Alright? And as mentioned earlier, we said that we are going to come back here to the discrete sampling. Why do we say so? And this is why we are talking about resolution. Alright, this is where we are going to talk about the resolution. The resolution defines that how many samples are you going to take. Alright, in this case we take more samples, so the resolution will be better. Because in current computers, you cannot take all, you cannot have a lot of samples, right? Because you have limited. Although you can take many points, alright, you can take many points and then eventually you will have this signal. But at some points, you cannot fully take on infinite points, alright? You cannot take on infinite points. And therefore this is why the resolution is limited. Okay, the digital has a limit of resolution, and what I just said is just in terms of sampling. But what I'm going to go more further is in terms of the explanation of beats. Alright, what is the definitions of beats then? A higher number of beats give us a better resolution, as what we have said, right? The beats itself is just simply how many sampling size you're going to take. Alright, if you take more sampling, then you're going to have more beats. Alright, so then we have limited beats. Okay, and so how does this beats go? Is that, for example, if we have a one-pin system, alright, the one-pin system is 0 and 1, or we call it a 2-bit system. This 2-bit system can actually somewhat deal with, for example, the input of 0 volts to 5 volts. I'll just change a different color. Alright, so this 5 volts, alright, input divided by the number of bits, which is 2, is 2.5. And therefore, this 5 volt signals can be re-represented as 0 volt to 2.5 volt and 2.5 volt to 5 volt. Alright, so this value is somewhat how many times, it's like a time step, so to speak. Okay, it's like a time step. Alright, so the larger the time step, the larger the time step, the more inaccurate it is. Alright, the more inaccurate. And for example, if you were to still doubt me, if I have now a 4-pin, okay, a 4-pin means that I'll have a 16-bit. Alright, because the equation itself, okay, 1 pin states that it's 2 to the power of 1. If it's 4-bit, then it's 2 to the power of 4, and therefore it's 16-bit. Okay, if I were to take the same input again, alright, input is 0 volt to 5 volt, so 5 divided by 16 is equals to 0.313, somewhere there. Alright, 0.313. So I can re-represent all this signal in terms of 0 to 0.313, then 0.313 to 0.626. Can represent this signal as 0.3, all of this, alright, etc. So this is 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit, all the way to 16 bit. Alright, so I can actually somewhat have more sampling or more discrete system to look at, and therefore I can better represent our signal better. Alright, and if it's a 32-bit, or in other words 5-pin, I don't know whether do we have 5-pin, but anyway, maybe 6-pin, okay, 6-pin. then we will have 2 to the power of 6, which is 64 bit. Alright, and therefore this is you can actually discretize the signal into more bits so that you can analyze each of the signal better. Alright, so you'll be more accurate, better resolutions and things like that. Alright, and therefore to summarize is that the continuous signal is simply analog, discretized or sampling and quantized are simply digital, and we explain what is the reason behind why we want digital. We want to convert analog to digital. What are the benefits? And then we describe of why is it that the digital has a limitation of resolutions, explaining in terms of the sampling, discrete sampling. Perhaps if you were to go in, you know that quantized is somewhat similar to sampling. Alright, and also we also explain in terms of beats. Alright, and therefore this is it. Next video, other stuffs. See you there.